Swayam Prabha. Digital India. Educated India.
Preparatory talk for the next topic, which will be discussing additive manufacturing of preceramic polymers to make polymer-derived ceramics. So if you don't mind, I will spend a few more minutes discussing preceramic polymers in general. And yesterday we looked at what are preceramic polymers, what kind of characteristics they need to have in order to achieve a high ceramic yield. We looked at what happens during the polymer to ceramic transformation, the decomposition of organic moieties with gas release, issues in terms of cracking and thickness of the part that you can obtain without defects. And then I introduce you to the possibility of mixing preceramic polymers with fillers. And besides thinking of fillers such as fibers or other materials that have a functional purpose, I discussed the fact that you can have so-called inert fillers, so particles that simply fill the volume of the body, and by eliminating part of the preceramic polymer in the final component, reduce the shrinkage, control the shrinkage. Another approach is to use what have been called these active fillers, which are particles that react to form new ceramic phases. And we looked at metal particles, and I mentioned that you can obtain a wide range of carbides, often together, or I would say always together with some silicides as well. And then I mentioned the fact that you can also go down this route to obtain not parts based on, for instance, silicon oxycarbide or silicon carbon nitride or silicon carbide, so carbon-containing phases, but you can also obtain fully oxide phases. And of course, there's a wide range of advanced ceramics that are fully oxide-based. In this case, you start by using some precursors for oxides that will then react with the silica coming from the decomposition of the preceramic polymer. And I should mention the fact that the silica that comes from the oxidation of the methyl and phenyl groups in the siloxane during firing in air is a type of silica that is highly reactive. And this means that, for instance, you can obtain mullite, so aluminosilicate phase, at much lower temperature with respect to starting from alumina powder and silica powder. If you do that, you need to achieve full mullitization, you need to go above 1500 degrees. If you use this approach, you can obtain 100% mullite at 1000 degrees. And it helps if you use a reactive form of alumina, for instance, gamma alumina, that allows you to do that. You can use it both in nanoscale or in microscale. So the features, advantages of the filler approach is that you can obtain monolithic samples with no cracks. You can control the crystal phases that you form depending on the amount of material and type of material and the firing conditions. Since you have a high loading of particles, cross-linking the preceramic polymer is not always necessary, which means that you can use preceramic polymers that are not tailored for setting reactions. The mixture, you can control the mixture reactivity and the reaction path and obtain, as I mentioned, phase purity. And of course, by modifying the composition, you can get different properties for your materials. These are a list of different oxide phases that we generated with this approach, and you can see that you can also obtain nitrogen containing compounds if you fire, for instance, in nitrogen atmosphere. And of course, all these phases contain silicon, but some of these phases have very useful applications, as I will show you. So I'm showing here some examples. Here you can see that you can form moonlight at low temperature. So this is the original paper from long ago, from the 1997, showing that if you use corindon as a particle for reacting with the silica coming from a preceramic polymer, you need to go to 1700 to obtain phase pure material. But if you use nano-sized oxide fillers, or if you use oxide precursor particles, or if you use a reactive form of silica, you can see here that we can obtain with gamma lumina moonlight already at, in this case, 1250, but we can go down even lower. And the activation energy for the reaction is much lower than what is typical for other approaches. We also made zircon, which is a very interesting material for high temperature application. So it's a zirconium silicate. In this case, we needed to control the phase formation using a sintering aid, a seed based on titanium dioxide. You can also obtain other useful ceramic materials still containing silicon oxide, such as cordierite, which has a low coefficient thermal expansion, so it's a good material for different applications, refractory applications. In this case, we were interested in foaming the material. This is the first example, but we are doing much better now, of course. This is very old, but we can generate a wide range of bioceramics with this approach. We can also use this filled preceramic polymer approach to make coatings. And in this case, we made yttrium disilicate coating on silicon carbide to protect from oxidation. And for Cylon, as I mentioned, you need to fire in nitrogen, and after firing at 1550, you can get phase pure Cylon. We also use this approach for joining. In this case, we join Cylon pieces with Cylon, and with this type of rig, so this is graphite, and if you put your material in there during firing, the material expands, but the graphite does not expand, and therefore it puts the material into compression, so you can achieve a dense, a strong and thin joint. You can see that the thickness of the joint is just a few microns. You can also make luminescent materials in this approach, in this case based on doped Cylon. And this is just to say that it makes sense to consider using preceramic polymers, but not simply by themselves, but also mixed with fillers. So let me just continue by mentioning some of the properties of polymer-derived ceramics, which justify our interest in developing components based on these materials using additive manufacturing. As I already mentioned, that they can have high microstructural stability. They are either amorphous or nanocrystalline. They have a high creep resistance. They have high viscosity, high oxidation resistant, high chemical durability. One interesting point is, for instance, the silica dissolves in highly alkaline solutions, and the dissolution rate for silicon oxide carbide in a highly alkaline solution is 10 times lower than that of pure silica. I mentioned that you can have some functional properties due to the presence of carbon nanoclusters, and you can have electronic conduction, You can have piezoresistivity, electromagnetic wave absorption, luminescence. I didn't talk about the structure of the silicon oxycarbide glass, but you know that in a silica glass, you have silicon oxygen, silicon bridging bonds. So the anion is oxygen, and the network has a certain flexibility and therefore a certain glass transition temperature. If you substitute oxygen for some carbon, I didn't mention the fact that when you pyrolyze a preceramic polymer, some of the carbon stays attached to silicon, some of the carbon phase separates into graphene, into turbostratic carbon. So you have carbon that is linked to silicon. So if you have a glass where you have a silicon carbon silicon bond, then carbon needs to link to other silicon atoms. And this leads to a stronger network, which reflects into higher mechanical properties, for instance, elastic modulus. So you know that for silica fibers, the elastic modulus is not very high. So people are interested in developing fibers with high elastic modulus. Rather than 70 gigapascal with a silicon oxycarbide, you can go up to 100 gigapascal. And the glass transition temperature is higher by about 200 degrees. So it's around 1200 degrees for silicon oxycarbide. You can, of course, I will show you, incorporate porosity into any of these preceramic polymers, and you can do that easily because they behave like plastics before being pyrolyzed. And people have been using them for lithium storage. Lithium ions intercalate into the turbostratic carbon phase, and has been demonstrated. So you can see here a range of properties for different classes of polymer ceramics. And you can see that you have a wide range of values that you can tailor with this approach. Here are some data, but we can skip the data. So before starting discussing additive manufacturing of preceramic polymer, let me just finish by mentioning that you can make a wide range of components using preceramic polymers by themselves or with added inert or active fillers. People use them for making powders, for making fibers. They use them for infiltration of porous bodies. They use them for coatings. They use them for making bulk ceramics, and they use them for making porous ceramics. So I don't think I want to spend too much time here. So I will give you this this material if you're interested, but I will just pinpoint some. I highlight some possibilities. Let's see if this moves. This is no, sorry. This is supposed to be a movie, a computed tomography of fiber mat produced by electrospinning. So we were the first ones to demonstrate that you can use electrospinning with a preceramic polymer and then convert the fibers into ceramic fibers. And in comparison to using a conventional polymer that has been engineered properly for electrospinning, the fiber size here, thickness is larger, because typically with electrospinning you can go down to a few hundred nanometers. We will not be able to go below 900 nanometers, but that's not necessarily a problem. And one of the interesting things of preceramic polymers is that, as I mentioned, you can embed different precursors for other phases. And for instance, if you add a metal precursor in the form of an acetate, then or acetyl acetonate, so you can have a solution that you can electrospin properly. During pyrolysis, copper not only copper ions not only coalesce, but they also get reduced to metallic copper. So in this way, you can make, in our case, nanofibers or submicron fibers decorated with metallic nanoparticles for catalysis applications. You can also do it with silver. And okay, so the CMC preceramic polymers have been used a lot also for making ceramic matrix composites. Here is some work that I did in the past on coatings, and there is one interesting point to make here. So no problems with making a coating from a solution of a preceramic polymer, but if you want to retain carbon in the material, since the coating thickness is very limited, we realized that using regular grade argon was not good enough because the little oxygen contamination would be picked up by the material. And if you use vacuum, then you can retain the carbon in your material. So I can skip these things. Joining already mentioned. So you can see all different shapes that can be obtained. For instance, we use micro extrusion for making ceramic microtubes, and you can also make multi-lumen microtubes, ceramic microtubes starting from polymers. So you can actually take advantage of all the possibilities that polymeric processing gives you. In terms of applications, I mentioned that CMCs are an important part of the use of preceramic polymers. And this is an example for a rotor for motorcycle brake system. These are high temperature sensors because these phases, silicon carbonitride, silicon oxycarbide, can operate at higher temperatures than other materials, ceramic materials, and still possess some functional properties that enable them to be used as sensors. They have been also used as a way of patching defects that are generated by impacts with dust. And this is some experiments that were carried out long ago in 2006 for repairing space shuttle tiles when the space shuttle was still operating. And the advantage is that you can put the material in place, you can cure it in place, and then it would self-transform upon re-entry into ceramic materials. So it will very quickly transform into a protective ceramic phase. This is some of the work that we are doing in collaboration with the other colleagues for electromagnetic wave absorption. And people have also looked at using silicon carbonitride coatings for protecting pacemaker electrodes. You know, pacemaker electrode, you need to screw it into the heart muscle, and the screw is based on the metal, and often you have bad reaction between the metal and the tissue. So by coating with an electrically conductive layer, people are able to obtain a safer implantable electrode. Okay, so I don't need to read the conclusions. So this was just to talk about the preceramic polymers, and now I will move towards discussing using additive manufacturing technologies for fabricating components based on preceramic polymers. And this morning I will discuss VAT photopolymerization technologies. I will give you examples of what we can do. We and other people, of course. Okay, we already discussed what preceramic polymers are. These are the different technologies that have been used together with preceramic polymers. You can see the type of feedstock that is required for making parts, the size that can be produced economically for the part, the surface quality that you achieve, and the printing resolution. And let me just remind you that cross-linking of the preceramic polymer is necessary before pyrolysis, unless you have a highly filled system to retain the shape of the printing component. And of course, a high ceramic yield is preferred. So we already know that in order to make, skip this. So we already know that in order to have a photocurable feedstock, you need a photocurable polymer. And if you want to use preceramic polymers, there are basically only 5 ways to do that. The ideal way is to get a commercially available high ceramic yield preceramic polymer that contains reactive groups. And unfortunately, such materials are not existing because you can have commercially available high ceramic yield preceramic polymers that are non-photocurable, or if they are photocurable, they contain vinyl groups, and those give you only sluggish reactions. So they're not really suited for additive manufacturing approaches. And there are plenty of UV curable, for instance, siloxanes. I mentioned that people use them, for instance, for conformal coatings on electronics. So you can find a lot of UV curable siloxanes, but typically they need a high energy for curing. But even if that's not the case, they are not tailored to achieve a high ceramic yield. As I mentioned yesterday, if you purchase a conventional UV photocurable siloxane, the ceramic yield is 7%. And this is, of course, not good. And it is related to the fact that these polymers have a linear chain. So this is the ideal approach that often has limitations. Of course, if you're a chemist, I'm not, you can synthesize your own photopolymer. There are examples in the literature of that, but then scaling up is certainly an issue. You can build a preceramic polymer structure using a thoroughly click chemistry. So you can use a sluggishly reacting photopolymer and improve the speed of the reaction using thoroughly click chemistry. But this leads to sulfur and oxygen contaminations. And we were actually the first ones to demonstrate that you can use photocuring to generate structures from a preceramic polymer using additive manufacturing. And we proposed 2 different ways. One is the chemical modification of a commercially available high ceramic yield preceramic polymer that is non-photocurable. And the other one is the blending of 2 polymers, preceramic polymer and a photocurable polymer. So the first approach is possible if you have a preceramic polymer that has some reactive groups. And we selected a siloxane resin that has a ceramic yield of about 85 weight%, and it contains cyanols, SiOH groups. And these are reactive groups, and you can use them for grafting a silicon-containing acrylate. So you can, in this way, generate, and this is a liquid, in this way you can generate a liquid single-source precursor that contains photocurable moieties. And in this way, we were able to obtain a single-source precursor with a ceramic yield around 65%. and I can skip this. You can see that indeed we have been able to print. This is just demonstration piece. The yellow color comes from a photoabsorber that was added in order to achieve a better control in the z-axis. The as printed material has no cracks or bubbles. The quality is very good. And you can see what happens during the polymer to ceramic transformation. You have the shrinkage, which is isotropic. In our case, we had about 25% linear shrinkage. And one interesting point is that since we photocure the material, we didn't have any softening, any melting of the polymer during pyrolysis. So this was very good to obtain. And you can see the quality of the printed part, very smooth surfaces. You can see the stair-stepping effect, but very limited in a very limited way. The layer thickness was 25 microns for these samples, and you can see that after pyrolysis, you retain the structure and the quality of the part. And the most important point is that you have dense struts, so the solid part is dense, and therefore the strength of the material is high. The second approach is actually more simple because it allows you to use any type of preceramic polymer. So we came up with this idea that if we can create a stable solution between a photocurable polymer and a non-photocurable polymer, and we photocross-link the polymer to generate a part, we would have a co-continuous network. On one side, the photocured network, and on the other side, the network generated by the preceramic polymer. And of course, you need, in order to have a correct phase separation, interconnected phase separation, spinodal phase separation, you need to control this mutual solubility and compatibility of the polymers in terms, for instance, of hydrophilicity and hydrophobicity. And you can actually follow two different routes. The photocurable polymer can be a siloxane itself, so it has some ceramic yield, even if it is very limited, or it can be simply an organic polymer. And in this case, the ceramic yield is 0, so it will completely disappear during pyrolysis. So we tested different preceramic polymers in different ratios, and we were able to print different parts. Of course, so this is the ceramic yield for the polysiloxane acrylate. You can see very, very low. And this is the ceramic yield, the TGA curve for the siloxane. And if you mix these materials, these are two different siloxanes. If you mix the materials in different ways, you can obtain a higher ceramic yield. Bear in mind that the actual ceramic yield for this blue line should be higher because these are solvent molecules that were not eliminated before carrying out this experiment, so the curve should be shifted upwards. You can see that we needed to learn how to control the printing characteristics. If we didn't have enough photoabsorber, we would overexpose the part, but by controlling the amount of photoabsorber, this is a cheap DLP printer. The size of the part is of the order of few tenths of microns. And by modifying the content of the photocurable polymer, you also change the exposure time that is required. This makes sense because the less polymer you have, the longer it takes to cross-link. And you can see that we were able to print. This is the pure photocurable siloxane acrylate, and the shrinkage is the linear shrinkage is very high, 70%, and the ceramic yield is very low. But since the struts are very thin, then you can obtain a crack-free part after pyrolysis. In this case, we mixed the siloxane acrylate with the high ceramic yield preceramic polymer, and you can see that again we can obtain good quality parts. In this case, the ceramic yield was higher and the shrinkage was lower. One interesting point is that with this approach, you do not need to cross-link the preceramic polymer, because what happens is that when the preceramic polymer softens at around 150 degrees, the photocurable polymer structure is still there, so it acts as a support for the preceramic polymer. And then with higher temperature, then you have thermal cross-linking of the preceramic polymer, and in that way you can retain the structure. So you can see here that if you look at the amount of photocurable material inside your feedstock versus the linear shrinkage during pyrolysis, and you can see that these are different materials, and the shrinkage was measured after drying and after pyrolysis, and that's the total shrinkage. But the main point is that, again, if you use only a polymer that has a limited ceramic yield, you obtain a very high shrinkage. If you use a lot of preceramic polymer and a limited amount of polysiloxane acrylate, you have a lower shrinkage. And the important message is that you know that when you use additive manufacturing, depending on the technology that you have a certain size specifications that you can achieve. So for typical DLP printer, you cannot go below 50 microns, say, of resolution in the XY plane. The thickness of the layer you can control more easily, but then, of course, smaller layers mean much longer times for printing. But in the XY plane, you cannot achieve features that are smaller than 50 microns. If you use a preceramic polymer that has a high shrinkage, then you can print 50 microns, and after pyrolysis, you get a much finer detail, because you can shrink that by up to 70%. So this is a good way for generating high precision parts using preceramic polymers by controlling the shrinkage. You can see different geometries. We are interested mainly in porous materials. Another non-trivial but interesting fact is that indeed you obtain dense struts. So we started from a green component that was a mixture of a volatile photopolymer and a high ceramic yield preceramic polymer. The volatile polymer is decomposed, but the preceramic polymer is capable of then forming a dense structure after the process, and this is non-trivial. We worked a little bit with Kathy Faber at Caltech and generated structures that were mixed Kelvin cell and octet cell design. And the reason for that is that from the mechanical point of view, if you test the parts in compression, a Kelvin cell is a bending dominated structure, meaning that the struts fail by bending, while an octet cell structure is a component in which the struts fail by stretching. So in terms of strength to density ratio and octet cell design is more performing. The reason for having a mixed structure is that we were looking at how the cracks would propagate through the structure, because when you change the mode of fracture, you have crack deviation and increased toughness. So this was a study that was conducted in order to try to achieve that kind of behavior. You can see that the surface quality can be improved by using smaller layer heights. You can see, again, very clear stepping effects and more homogeneous surface on the left for the smaller part. This is just an example. This is not the best example. It was 4 years ago, now we can do much better. This is silicone-based, no, this is sort of silicon oxycarbide-based ceramic that as a component that has been used for electromagnetic wave absorption. That's my daughter, and this is some silicon oxycarbide jewelry that we made for her. She's not wearing them, anyway. I mentioned that you can generate parts by using Preceramic polymers filled with other particles, other fillers. And in here, we demonstrated that you can generate mullite parts by printing silicon resin with gamma lumina nano powders. And that's supposed to be a filter part. In my lab, we can print from the submicron scale to the meter scale using a wide range of technologies. And one of these technologies is two-photon polymerization. I discussed yesterday a little bit this approach. You basically write inside the volume of a vat, but you need to start from a substrate. And here you can see that we printed the same Kelvin cell type of structure, but if you look at the size, you realize that the resolution is much higher. And I don't know if I can see, yes. So this is the actual printing of the part. So we were able to develop what people would call a photoresist that was efficient enough to be able to be printed in this approach. So we were able to generate parts that were based on a Preceramic polymer. And then the next step was to subject the part to pyrolysis. And of course, you have a substrate, which is silica quartz, that doesn't shrink, while the Preceramic polymer shrinks. So we thought at the beginning that we could accommodate for the differential shrinkage by attaching the part to some extensions that would move, contract during pyrolysis, but you can see that we were not successful. So we followed a different approach that was actually proposed by a different person for carbon-based materials, not for Preceramic polymers. And we built the part on a pillar made of the same material. And what that does is that, so this is the size of the original pillar, and this is after pyrolysis. And if you control the ratio between the width of the part and the height of the part, then you can, at the end, achieve a component with the correct shape after pyrolysis with no distortions. So this is nice. You can make some micron features, ceramic features on top of surfaces in this way. And this is also another video that shows the testing under the SCM on this part. The part was about 80 to 90 volume percent porous, and the strength was 1.5 5 gigapascal compression strength. And the reason, of course, for this such a high strength is related to the fact that being the material structure, the nanoscale, then the critical floor size was very small. And you can see before fracture and after fracture the part. So this approach is nice. You can make nice looking parts. We could have built a wide range of different shapes and components, but you have this issue of the part being attached to the substrate. So we came up with another approach, which was the hybridization of 2 technologies, VAT photopolymerization based technologies for fabricating multi-scale ceramic components. So you know that DLP has the advantage because it generates macro components, freestanding, that you can handle them easily, but it has resolution limitations, 50 to 100 microns. 2-photon polymerization has a very high resolution, but can only make micro components connected to glass substrates and typically non-detachable, especially after pyrolysis. So by combining these 2 technologies, we were planning and aiming at achieving the best combination of characteristics. So basically what we did was to take a 3D printed part and build the same structures on top of that using 2-photon polymerization. And this is as printed, there's no detachment, good surface integration, and stable combination of materials. And after pyrolysis, since the material for the base scaffold and the surface features was the same, we have the same shrinkage, and there's no detachment after pyrolysis, no shrinkage mismatch. Of course, this type of component doesn't have any practical use, but you can think of using this approach for making, for instance, nozzles. So we can make part of the nozzle using DLP, and we can make it in macro scale, and then only the tip we can make using 2-photon polymerization. And in this way, we can achieve very unique parts that have not been possible to obtain using other approaches. So let me talk now about volumetric additive manufacturing. So we are still talking about photopolymerization approaches. And the approach that we are using is based on a new technology developed by a German startup called L03, based in Berlin. They published a paper in Nature in 2019, and we purchased this printer in 2021, and we were the first ones to use this for making ceramic materials. So this is a volumetric additive manufacturing approach that is based on a proprietary photo-switchable initiator that is a dual color material, because the system works by exploiting the linear excitation by intersecting light beams of different wavelengths. So you have one UV source, which is a laser, and a visible source that projects the image of the material that you want, or the component that you want to print. And when these 2 light beams meet, they trigger the photoinitiator, and they polymerize in situ. And you can do this inside the volume of the liquid. So you have the local polymerization inside a confined monomer volume. There is no oxygen inhibition, because you are printing not at the surface of the liquid, but you're printing inside the liquid. And you do not need to rebuild any layer like you do with DLP. So it's a fast technology, and printing rates up to 1 cubic centimeter per second are possible, and resolutions can be down to a few microns. They actually have a better version that we also purchased for this printer, and now the resolution is down to 5 microns. So you have these two photo initiators. So you have this 2-color photo initiator that is first added by the first UV wavelength, and then the absorption of the second wavelength initiates the photopolymerization. This is a type 2 photo initiator. And basically you can see here you have a cuvette with your photocurable material. The light sheet, UV light sheet comes from the side, and here you are projecting your image using a visible light, and the cuvette moves in this direction. So basically you are, this is a linear volumetric additive manufacturing technology, because you are building in a continuous way inside the liquid. Besides using a very specialized and expensive photo initiator that you can purchase from the company, there are complex requirements for the photocurable fluid. It needs to be compatible. This is a type 2 photo initiator, so it's highly alkaline. You need to use a photopolymer or a system that is highly viscous. And the reason why you want to have something highly viscous is that, first of all, you don't need to deposit any layers, so viscosity is not a problem, but you specifically need a high viscosity, because when you're printing the part, you are changing the density. And if you are doing that in a liquid that is non-viscous, you have settling of the part, you have movement of the part, you cannot get a high resolution. So your photopolymer needs to, or your feedstock needs to be viscous. And there are advantages with this high viscosity, because the printed part is supported by the unreactive material surrounding it, so you do not need any supports for overhanging features. The photopolymer needs to be highly reactive, because the radiation has to go through millimeters of the solution rather than simply microns, like in conventional photopolymerization approaches. And therefore, you need to have enough intensity where the light beams meet in order to be able to trigger the photocuring. I mentioned that you can print very fast. One additional requirement is that the strength of the green body that you form needs to be high, because you need to then extract the part from the viscous liquid. You need to remove the viscous liquid from the part, non-reactive viscous liquid from the part without damaging it. So you need to find the correct materials. And besides being possessing high reactivity, the material also needs to be highly transparent. So this volumetric approach is not well suited for particle containing systems, and we wanted to exploit it for preceramic polymers, exploit the advantage of using simply a solution. By the way, we are currently working on using colloidal suspension. So you can use ceramic particles, but only if the particle size is below a few nanometers. So our particles range from 5 to 20 nanometers. And in that case, you can achieve enough transparency for printing. So we wanted to use this approach for making parts using precursor-based approaches. And we tested preceramic polymers, and we blended highly reactive UDMA photopolymer, which is something that dentists use. Okay, all the dental resins are based on often on UDMA, and we used a high reactive high ceramic yield preceramic polymer, And of course, we are interested in having as much preceramic polymer as possible. But and you can see that if you start adding a lot of preceramic polymer, then the transmittance of the solution decreases. This is because we cannot use a solvent because they would decrease too much the viscosity. So we cannot use a neutral solvent to dissolve the solid silicon resin into the UTMA liquid photopolymer. So we have phase separation and some issues with transparency, but the main point is that you need enough transparency for printing. So we could print with all of these systems, but the best ones were the ones that contained the least amount of preceramic polymer. And of course, depending on the content of photopolymer, you have different ceramic yields. But we were able to find systems that enabled us to generate good parts. The cuvette is 1 centimeter in width, and this is a square one. The UV light comes from the side, but the cuvette, so that cuvette is has a square cross section and is placed in like this in the printer. But we can also use cuvettes that are 1 centimeter in width and 10 centimeters in length. So in this way, we can make much larger components. And for polymeric systems that are highly transparent, they are now printing in a cuvette, which is 5 centimeters in width. So we are still trying to improve the transparency of our system to generate larger components. But you can see, I hope, the level of details that we can achieve with this technology. And being this VAT photopolymerization volumetric approach, we can generate, for instance, structures like a ball in a cage that you wouldn't be able to generate using DLP approaches. So in this case, for these materials, we have a high content of photopolymer. And then at the beginning, we had issues in terms of converting the printed part into a ceramic part. We had issues with gas evolution and cracking. And we tried, of course, to control the heating rate, but beyond, we were not able to solve the problem until we decided to use some additives that have the purpose of generating transient porosity. So by using, for instance, something like camphene, you can decompose camphene at a temperature before at a temperature which the photopolymer has not yet decomposed. And this means that you are generating an interconnected continuous network of pores. And then when the photopolymer decomposes, this porosity enables the gases to be eliminated. And in this way, we can obtain crack-free parts. Still talking about UV or photo curing of systems of preceramic polymers, we developed, this is one first approach, we have better systems now. We developed a possibility of extruding preceramic polymer system that is photocurable. And in this way, by activating the curing, we can freeze the filament precisely and quickly in space, achieving structures that you wouldn't be able to generate using direct inviting. If you use direct inviting, it is basically impossible to have a rheology of your material that enables you to retain that type of structure. But with UV, almost instantaneous UV curing, you can do that. We also have implemented that on top of a robotic arm. Okay, yeah. So we have an extruder and we have a UV lights at the end of the extruder. And the advantage of using robotic arm is that we can generate, since it has 6 axes, while a Delta printer only has 3, we can generate parts with a shape that you wouldn't be able to obtain using conventional direct inviting. And again, we try to, you can see that the head of the extruder tilts, and the reason is that we try to obtain homogeneous irradiation of the strut. Otherwise, we have issues in terms of differential photopolymerization degree of the material. And you can see there the part being printed. And then, of course, we take the part and we pyrolyze it. So in conclusion, I can say that Preceramic polymers plus fillers offer the potential to produce relatively easily ceramic components in a wide range of compositions using a wide range of additive manufacturing technologies based on photopolymerization. We are mainly interested in highly porous structures, and the reason why we're interested in that is that additive manufacturing allows you to generate non-stochastic architecture, so regular porosity, metamaterials that have advanced properties given by the structure. And we can combine DLP macrofabrication and two-photon polymerization in order to obtain micron-size surface structuring of centimeter-size objects. So we can do hybridization, and volumetric printing is possible. So this is the end of the presentation concerning additive manufacturing of preceramic polymers using VAT photopolymerization technologies. And I didn't want to make this all about myself. If you look in the literature, there are now quite a lot of people that print parts using preceramic polymers, but we were the first ones to publish concerning VAT photopolymerization, DLP, and also the first ones to show that you can do UV-assisted direct inviting of preceramic polymers, and the first ones to do two-photon polymerization, and the first ones to do volumetric additive manufacturing. That's why I'm talking about myself. But again, if you look at the literature now, there are quite a lot of people, especially in China, working on these approaches, and their main interest is functional material sensors, functional components, sensors for high temperature applications, or electromagnetic wave absorption components.
Sir, good morning, sir. Sir, I saw you have fabricated some of the lattice structures using this one.
Yes.
So generally we prefer lattice structures that should able to undergo some amount of deformation. Since we are printing ceramics for lattice structures, so what is the purpose of doing that, or do you have any intended application?
So with ceramic metamaterials, you can generate components that are efficient for electromagnetic wave absorption or for filtration. So we are interested in those type of applications for generating scaffold type structures. We have actually moved away from making scaffolds, and we are typically working with triply periodic minimal surface structures, because they further optimize. They're based not on rods, they're based on sheets. So we are generating what are called cellular materials, so cellular materials based on sheets, and they have better mechanical properties than strut-based structures.